Hi everybody, welcome back to Calculus 2 by Example. In this video we're going to talk about how we can calculate the arc length along a curve. So what we want to do is I want to say start at x equals 1/2 and go to x equals 2 and ask how long, how far is it if I follow this curved line. Okay. So if I imagine that I'm a little man, a little mountain climber, climbing down this slope and then up this slope, how far do I have to walk along that curve? Just like with everything else in calculus, we're going to find this value by starting with an approximation. We don't know yet how to find the length along a curve, but we know how to find straight line distances. So what we do is we break this curve into a number of straight lines. So here I broke it into 1, 2, 3, 4, 5, 6 straight lines because I can find the length of those straight lines using the distance formula that you might have learned back in algebra or geometry in high school or something like that. Okay, so I can find the length of a straight line. So instead of trying to tackle the problem directly, I start with the straight lines. I add up all those little straight lines, and then I could get better and better approximations by using more and more straight lines. Okay, if we stop and look at a single straight line, I could form this little right triangle. The width of the triangle, the horizontal width, is delta x. That's the change in x from one point to the next. The height of the rectangle is delta y. That's the change in height from one point to the next. And then the length of the diagonal, which is really the distance we want, or the length we want, is going to be the square root of delta x squared plus delta y squared. And we could find that using the Pythagorean theorem. All right. So this formula is the formula that we would use to find the length of each of these individual little lines. Okay. So to find the distance, or to approximate the distance from the first point to the last point, we're going to add up all those little delta s's. We're going to add up all those little distances from one point to another, but then we're going to take the limit as the number of lines in our approximation goes to infinity. So what we've done is we've broken that line, we've broken that curve into infinitely many pieces, and we're adding up those pieces. So we're getting a Riemann sum just like we had when we were calculating areas. So once again, we're seeing in calculus how we start with an approximation that we can calculate using the distance formula in this case, and then using limits, we improve that approximation incrementally until finally we're going to get the value we want. Okay, so here are some refinements. I can replace delta s with what it's equal to. I'm going to divide everything inside by delta x squared and pull the delta x outside. It goes from delta x squared to delta x because I'm taking it out of the square root. But if I look at what I have inside, delta y over delta x is the slope of that line. And if I take the limit as the number of lines goes to infinity, that slope is going to become the derivative. So when I move from the Riemann sum to the integral, the change in y over the change in x becomes the derivative. And this is one of the reasons that one of the first videos I did in this series focused on the definition of the derivative. Okay, so this is the formula that will give us the arc length of this curve from 1/2 to 2. So our limits of integration are 1/2 to 2, and this integrand is called our arc length differential. Okay. And so that's how that's sort of the basic idea behind calculating arc length, and that's kind of independent of what the function is. There are some variations on this if x is a function of y instead of y being a function of x. Or there are variations on this if x and y are both functions of a third variable t, which if you have a function describing the position of something over time is something that can happen occasionally or frequently. Okay, so that's the last video on integration applications. So we talked about areas and volumes and arc length. Those are sort of the basic applications that I tend to cover the most when I'm talking about applications of integration in Calculus 2. In the next video, we'll start talking about integration techniques. All right, I hope you get something out of this video, and I will see you later.